the approach is now that you can actually look at smaller numbers of patients that you could realistically acquire in a phase 1.
On the topic, and so our goal is how do we drive these signatures to the clinic, define minimal signatures.
That where the cells sit in tumors will help to us understand why patients respond to therapies.
Panel discussion. Okay, so maybe let's do a round of introductions. Maybe you start from that side. Well, Arutha, we already talked a little bit about you, but talk a little bit about kind of what you're doing at Queensland that you have not mentioned. Maybe the support you get from your ecosystem, stuff like that. Yeah, is it working? Hey guys, it's not working.
There we go.
Okay.
So I lead a spatial multiomics lab at the University of Queensland. We've established the Queensland Spatial Biology Center, and so that's purpose design. The goal is, can we use spatial biomarkers to really move the needle for translational biomarker studies? And so we're integrating, traditionally we look at retrospective cohorts, but the goal here is, can we identify signatures and then go validate it in proper clinical trials, in prospective trials. There are ongoing studies in the lab, and the lab's probably published 30 to 40 papers in the last couple years on the topic. And so our goal is, how do we drive these signatures to the clinic, define minimal signatures, and then really move it towards CDX-type assays.
Hi everyone, I'm Laura Dillon. I'm a Senior Director Partnership Strategy Lead at AstraZeneca. My training's in bioinformatics, but I've been working in biopharma for the last 15, 20 years, specifically in the translational medicine space with a focus on digital pathology, molecular imaging, and radiomics. Right now I'm leading a network of academics at AstraZeneca. We're really focused on identifying how we can use research, it's translational and basic research, to understand and inform strategy for development of our drugs. Using spatial biology is one of the things in our toolkit to do that, particularly multiplex immunofluorescence and spatial transcriptomics, but also other methods.
Chakra. I'm actually a colleague of Tullia up until recently. I was a professor in the Department of Computational Biology. And a lot of this work happened thanks to funding from NIH. And then at some point in time, just before COVID, we spun it off, and then I took a leave of absence, and then be in the company.
Can you hold the mic closer? I think it's you need to hold the mic really close, it looks like. Can you guys hear in the back what he's saying? No? Okay. So.
Hopefully I don't have to go again.
Hello? Okay, fantastic. I'll be very loud. Mike Surace. I am also at AstraZeneca, and I have a couple of different roles there. One is that I'm the translational medicine lead on a couple of engager and circuit programs where we're responsible for developing strategies for patient selection. The other is kind of the one that's more relevant, which is almost everything multiplex in the area of translational medicine is to one degree or another my area of responsibility. So that's designing, developing panels, validating them analytically, but also looking for solutions for analysis. And I think we're in a very interesting time where we're getting to a point of actually having line of sight on being able to put multiplex into the patient selection space, and that's one of my key focuses for our emerging programs. I am going to be cognizant of the fact that we don't have unlimited time, and I'll pass the microphone to Tullia.
Hi, my name is Tullia Bruno. Hopefully that's loud enough. I'm an assistant professor at University of Pittsburgh and UPMC Hillman Cancer Center. I was pulled into the spatial biology space because my research program focuses on tertiary lymphoid structures, and you can't study TLS in solid tumors without doing imaging in spatial transcriptomics and proteomics. I'd also like to echo that the other reason we really got into this space is because it's very, very clear that where the cells sit in tumors will help to us understand why patients respond to therapies or don't, as you're seeing in some of the data that was presented. So that's a lot of what we do in the lab now, thinking about what happens in treatment-naive patients versus what happens when a tumor microenvironment is treated and reshaped by a specific therapeutic.
Terrific. Have you introduced everyone here? Yes. Okay, fantastic. As I said, I saw around 35 to 40 booths here talking about spatial biology, many of them talking about analytics at this point. but the adoption still remains fairly low across the board. So maybe Tullia, since you work across academics as well as you interact with industry, let's talk a little bit about the adoption and what might accelerate that and what we have learned from genomics, really, for adoption of the technology.
So I think that the spatial biology and transcriptomic, all that space is being really well adopted by academics. I think that what we've been really trying to move past, which I think your group is doing and others, is you've generated this really beautiful picture from a patient tumor. Now what? So how do you analyze that? How do you garner as much information from that so that you can understand what's happening in patients and patient cohorts? I think that, and I think my industry colleagues are in a better position to say where the inertia is or where things are headed, basically for this in the industry side. But I would say from the clinical side, now that we're working in a lot more clinical trials, a lot of this is finding the right markers for the samples that you're getting, right? And I think I see a lot of people shaking their heads. So a lot of what was shown today for me isn't going to work because I'm not going to capture a TLS with a small needle, fine needle aspirate, or a biopsy, right? So how do I get creative in thinking about what I've learned spatially and then applying that to a clinical trial and making that more high throughput, right? And I think that's what a lot of academics think about when they're thinking about clinical trials and also thinking about scaling for these sort of efforts, because it's something that takes a lot of time and energy and money. So I think those are the two places that kind of have been the I guess, restricting it being further integrated into clinical trials. But what I will say is that I'm seeing it more and more. And so I actually push for people to do this because they can usually get more FFP tissue than they can fresh, for example.
Thank you. So, Mike, since you're from AstraZeneca, give us the perspective from the industry about the adoption. How do you accelerate that? And I think you've been a champion of this, I think, for the last 5 years at least. And so you can talk a little bit about the bottlenecks that maybe you're facing, whatever you can share.
Yeah, I think what I'd like to say is that the key to adoption, especially on the industry side, is to understand what incentivizes projects to use these types of technologies. So in the context of the emerging synthetic immunity and expanded sort of second generation immune oncology assets, I think it's always a mistake to lead with the tool first, right? So there was a bit of a rush maybe 5 years ago, and we started running multiplex immunofluorescence on everything across a wide variety of trials. And there's a lot of utility to having consistent data across trials, especially when you're talking about a family of assets. However, I think in a lot of cases we found that the bottleneck was, of course, analysis, which I'm very pleased that there are emerging solutions that are available outside of AstraZeneca to smaller companies like biotechs now. But I think the key is to make sure that you have line of sight to impact on the study, especially for actionable insights to make decisions on whether or not the study proceeds, or whether or not you think you understand the MOA, or whether or not you have a better view on pharmacodynamics. So I think that adoption is not what I would the rate of adoption is not what I would consider to be the rate limiter. It's the rate of being able to turn good data, right? Often you have good data into something that matriculates into impact on the study. And I realize I've said that 3 times. Maybe that's the right number.
Thank you, Mike. Maybe Laura, since you've been both in large companies as well as in smaller companies with Incendia, do you see any differences in terms of the technology moving in smaller pharma versus large pharma that you've experienced in the past? And in general, what's your take about adoption?
I mean, there's certainly a lot more stakeholders to align in large pharma than in small biotech. You can move very fast in small biotech, which is quite nice, but being in a larger environment, you have access to potentially to more resources. Just to build on what Mike said, I think the other real big challenge, as we're getting that line of sight for, I'm going to do this experiment to get this answer, which is going to inform how I do my next trial, That's really the type of thing we need to be able to see. But an important additional component really is the timing. And I think that's where a lot of these technologies are so challenging, is that if you have to get your phase 2 or phase 3 data and be doing the experiment in that setting, the ship has already sailed for being able to get to the market. And so I think that's why what's exciting about some of the approaches now, that you can actually look at smaller numbers of patients that you could realistically acquire in a phase 1, starts to make that a little bit more tractable, so that you can make those decisions moving forward in a timely manner to actually impact your drug development pathway. And so that's I think a thing to keep in mind as we're designing these experiments, is how can we actually make sure that we're hitting the outputs when we need to hit them, aligned with strategy in a way that's line of sight and can be communicated across a multifunctional organization, all the way from the early researchers who really interested in understanding mechanism of action, but also all the way up through regulatory, commercial, bringing everybody along.
Yeah, and Laura, you've been the first ones to really evangelize this whole idea of starting with the high plex in phase 1, 2, and then getting to a much lower plex.
Very happy to see that on your slide.
Yeah, finally we are doing that, right? So thanks again for exhorting us to do that many years ago. Arutha, you work a lot on clinical trials, which is a little unusual for an academic, lab. But I think that's been the key to your success, because it's not N of 1 that you're dealing with. You're dealing with hundreds and thousands of patients, and your results really have shown the kind of credibility that rarely you see from academia. Go ahead.
Yeah, I think one of the challenges for spatial has been a lot of N of 1, N of 2 studies. Look at my pretty pictures, and it's great as a sort of a undergrad study, but the challenge is you're understanding the biology not at scale, and so how do we identify the patterns associated with those clinical endpoints? And part of the challenge for us over the last 2 years has been, how do we access cohorts from around the world to be able to validate these signatures, which is what's been part of the challenge. But I think everyone's realized that you can't have single site studies. You need to really be able to, get a cohort from Yale and Brisbane and India and so on, and be able to validate your signatures. And so we're doing all the sort of discovery work retrospectively, but we're also now plugging into prospective clinical trials. And I think that'll really showcase the power of how we can scale these. One way to do it is using tissue arrays, but there's a trade-off there. But I think we'll make some insights into that.
Thank you. And maybe you're also in a unique position to answer this question. I mean, everyone nowadays claims that they're doing AI, right? I mean, I'm sure that you talk to many groups. There are people in academia doing AI, at least they claim to, in all the big pharma companies, big AI groups, foundation models and whatnot. What I don't see is a lot of talk about integrating the cancer biology and AI together, and that's kind of what we've been doing right from day one. Maybe a few comments on, how the AI approaches really differ and what exactly needs to be done.
Yeah, it's a double-edged sword, isn't it? I think we want to get there really quickly, but there's a lot of ground truth. There's a lot of work that we need to sort of do initially. Part of the work we're doing at the moment is integrating your multiplex data with your H&E. I think that's a good starting point. And then you build your omics sort of cloud, and then you can do your imputation and all of that. I think before we get to the spatial agent sort of today-ness of it, I think there's
that's a new buzzword. Everyone is doing spatial agents all of a sudden.
I think there's a ways to go, and obviously, part of the challenges is working with pathologists, really trying to be able to understand, are these cell types we're seeing, are they real? Working with immunologists to really validate them. I don't think we're there yet, Dusty, maybe in a couple of years, but I think there's a lot more groundwork to do in this space.
Maybe Mike Surace, you've been, kind of you've been futuristic in your approach from as long as I've known you in terms of where AI can go and what AI can do. Maybe a few comments around what you see at this point across the board.
Sure. From my perspective, trying to identify what this minimal signature is going to be. We think about that in the context of a single project, and it makes a lot of sense, right? We have a large number of targets. We identify a signature, and then we duplex that by there's various methods of minimizing that down to something that's actually deployable. When I think about sort of reasonable applications of artificial intelligence from an agentized standpoint or a mixture of experts approach. I think that I agree with Arutha that we are not there yet. We have a long way to go. We're in a proliferation stage of technologies. I think that the folks who sort of sit and wait and watch what happens are going to very much be at risk of missing opportunities because the rate of advancement in artificial intelligence, just the capabilities of the tools that we all use every day, of the large language models, is so fast that this isn't something that you can wait, look, and pick up once it's matriculated to some sort of point of maturity. This is something that I think we all have to participate in the development. So the way that we're leveraging this in AZ is broad and deep. I'm sure everyone saw the partnership announcement recently between AZ and Tempus from a data science standpoint. That's one example of a commitment that we're making. I think it's also manifesting in smaller ways, such as our approach to identifying multiomics signatures for patient selection, which is at its very early and nascent stages, but is entirely built on a variety of artificial intelligence tools. So I think the short answer is that we're in a proliferation stage, and there's going to have to be novel methods for validating approaches, and then a pruning stage where we coalesce around a couple of key tools and approaches. But the way forward is currently unclear, but there are many opportunities.
I'll come to Chakra in a second, but Tullia, from your standpoint, what do you see in academia? By the way, Chakra came from Jeff Hinton's lab around 20 plus years ago, and he's the one that's kind of incorporated the explainability and cancer biology into the AI algorithms that we have. But we'll come to that. And Chakra, think about the futuristic. What's next? Tullia, go ahead.
Yeah, I think the AI track of trying to analyze samples and really do it this way is going to be something that happens over a very longer period of time. I agree with Mike. I think we want things to happen like yesterday so that it makes it easier to understand what patients should go on which trials, makes it easier to analyze patient samples and bulk predict what's going to happen. But there's just so many different ways to come at this, and there's so many different algorithms and ways in which people are modeling this. I do stand true, though, that I think that the biology that's present in the patient has to drive the AI. I know there's a lot of new kind of let's hypothesize or predict this cell from not thinking about the biology. I think that's going to be really crucial and instrumental, and I don't think we can just generate everything by AI and then hope that that's going to be the answer. I think there has to be a very clear back and forth between the two. That's the one thing that I've seen from those models that have come out recently.
Chakra, future. What do you see happening? The evolution of AI, multimodal data, foundation models, spatial agents. What's your view?
Maybe two comments. And
Louder, Chakra. Louder. Sorry.
Two comments. One, I think if you're familiar with Bayesian thinking, what Tullia just said was about there's this idea that you already know the biology, you want to know if the data verifies it or not. That's like finding the probability of the data given the biology. But what you really need is you want to compute the probability of the biology given the data, because that's the only way you get to this emergent biology. And this is where all these ideas, all the new ideas come in. You'll say, what if I build you a very large search space? So all the foundation models, say the LLMs and everything, which is great. But somebody has to go and verify. So I don't think so in this domain, you could talk about AI if it's not actually coming from an immunologist or a pathologist who actually have feel for the experiments, have a feel for the quality of the data, know the pain of actually generating the data, and then if they can articulate how AI is helping, then I would imagine that's a good day. And I think that hasn't happened yet, wherein somebody can actually assure you that these are the things that could come out, and here's a small set of hypotheses that I would like you to verify, and that they could explain that to an immunologist or somebody who's actually working in the lab. So you cannot build a foundation model if your data is no good. And if you have issue with the reproducibility, so that means one data set is very different from the other, where is this foundation model going to go? But in many ways, it's all good ideas. If it's about generating hypotheses, generating lots of them, pruning them, fabulous, bring them on. But I think being divorced from experiments, I think it's a danger.
Thank you, Chakra. You know, Sam Hanash, who was there till a few moments here, moments back from MD Anderson, is someone that pioneered liquid biopsy almost 30 years ago. He was the first one to show that you can see stuff in blood way before radiologically a tumor manifests itself. And he's been pounding me to integrate spatial biology and liquid biopsy, and that's why I want to ask Arutha, who has worked on both sides, is there some interesting possibilities of integrating liquid biopsy and spatial biology? And we know that there's some activity out there in the M&A space also kind of mimicking that. So let's talk about that.
Yeah, that's what curveball I didn't see coming. I mean, liquid's great. I think MRD, ctDNA, EVs potentially. I think CTCs are technically challenging. They're rare to find and so on. Liquid definitely has a use case. The challenge is when you identify the change in the blood, but you don't have radiographic data, it's not actionable. And so it's part of the reason I left that field and moved into the tissue space, because we know what we're looking at. And so I think in the future, ideally, how do we do a foundation or garden, tissue and blood and correlate those, that'll be sort of the ideal world. I don't think we're there yet. There's a long way to go. But also, there are signatures we can identify in the tissue that we can mine for in the blood. It'll be highly diluted, but you can, so look for those markers. And so that's the space that we're interested in. Can you do sort of high-plex proteomic profiling of tissue, identify certain targets? There are assays where you can identify, TLS-like signatures in the blood, which, baffles your mind that you can identify. But if it's there, can we find it? And I think in developing these studies, we need to start to biobank tissue and blood from matched patients. And I think everyone is sort of doing that. And then there'll be a space in which we'll be able to execute on both sort of domains.
Thank you. And Tullia, I mean, you've been one of the pioneers in terms of looking at multimodal integration of different modality data. So PET and spatial biology, you want to talk a little bit about that? But that's brand new.
Yeah, so I do want to just say one thing based off what Arutha said. I think the other effort we're making specifically in the TLS space that could also move into like a systemic in using ctDNA is thinking about how the tumor pushes TLS biology and how the tumor pushes the immune response. So we've got new data showing mutational differences based off of when you have a TLS and you don't have a TLS, and then we can then go back to the tumor and say, does that mutation then track in patients? So I think we're a little ways off, but I think that we can also use the tumor to understand the immune, which is, as an immunologist, I know I'm not supposed to be saying, but it actually is the truth, and I've drank the Kool-Aid a long time ago. So you don't have to worry about convincing me about the importance of thinking about the cancer type as well. As far as PET imaging and things go, one thing that we're thinking a lot of from the forefront moving forward, and as I mentioned, I'm very TLS centric, so that's my neighborhood that I think about a lot. We have been thinking about how do we look at these structures in 3D in patients moving forward, right? And so if as hard as 2D is and processing all those images and getting those large data sets together, which, as mentioned, Arutha has probably done this the best out of most that I've seen. There's still that complication in 3D that you can do even less, right? And so finding a way to look at things in 3D, particularly that are important, such as like high endothelial venules, which help with TLS but help with trafficking of immune cells in general. I think that will be the new frontier, and there's things we're working on related to PET imaging in that space, first in mice, but then thinking about moving into people moving forward.
Terrific. And I'm going to open up this last question for everyone. There's a lot of avant-garde topics coming up at the moment, like AI virtual cell, right? From the Chan Zuckerberg Institute, there was a paper from Stanford, and with 40 other authors around that. So this is all going to a point, can we really simulate clinical trials? Can you run in silico clinical trials ultimately with the network biology that you're exposing from all of this stuff? Arutha, you want to start, and then we kind of just come all the way through back?
Yeah, it's challenging, Dusty. I think it relies on the training data set you've used to really enable that. A lot of the data sets or the models out there today lack clinical annotations, and so the model's developed, but it's developed on no clinical endpoint in that data set. And so, whilst the model exists, there's no utility to it today. But I think, again, looking at the future, this is a space, this will
Address for a second the universality that you're seeing of some of these biomarkers in combination with others and interacting with each other across different cancers that you're seeing. We talked this morning about lung and head and neck, and what are you seeing very quickly?
The signatures we're seeing that are associated with resistance or sensitivity aren't tumor specific. They're almost pan-IO specific. And so that's really interesting to us. Some of the trends we see in lung cancer, we see in head and neck, we see in cutaneous skin cancers, and we think that's across the board. So some of those signatures of resistance seem to hold across tumor types, particularly in the therapeutic space. So whether it's chemo or IO and so on. So we're starting to think of these signatures as sort of a tissue, sort of a tumor agnostic biomarker. And we think it defines fundamental processes of resistance linked to metabolism and so on.
We're kind of out of time, so quickly, any comments? Anyone else? Go ahead.
I just want to stand up for foundation models a little bit after Chakra is so mean to them. So I think all of these different approaches have a place, certainly. I think to your point, we need to make sure that we're training the foundation models, or that the data that goes into them is appropriately broad. And Arutha, you spoke to that as well. But really, like, being able to, again, get that timing thing to link up by needing a smaller number of patients, and that's really where those foundation models can have a really important thing. But as we are thinking about going from that broad range of biomarkers down to the smaller amount, we also have to think about how we can get those. And this is where H&E based biomarkers could certainly play a role, because everybody in their gets an H&E, absolutely. This is where the serum biomarkers or even the PET based ones are so important, because those kind of less invasive, non-invasive type of methodologies are indeed what's better for patients. And so it's hard to talk about these in generalities, because like every use case is a different use case and needs a different answer. But I think there's roles for all of this, and certainly the technology we're talking about here today is hugely impactful for helping to understand that kind of broad space, so that we can understand the biology and then go back and really drill down on, okay, how can we come up with an actionable plan that we can deploy in the clinic to bring drugs to patients, not just in clinical trials, but actually in clinical practice.
Thank you, Laura. Mike, 30 seconds, you want to use?
Yeah, I'll be as brief as I can. I think just quickly on the question of an in silico clinical trial, I think it's not only possible but inevitable, but it's contingent on a model that is validatable, sufficient processing power, and sufficient data to train that model. So foundation models are an example of something that can be trained on disparate and deep data that's not necessarily all relevant to the question, but then you can use those to answer questions that were not part of the original data set with relative utility. So the short answer is yes, but the longer version of that is, I think it's contingent on substantial advances that I expect, but when those will matriculate.
Thank you, Mike. Thank you. Well, as Yogi Berra says, prediction is always difficult, especially when it's about the future. So on that note, thank you very much. Really appreciate your participation, and a big hand for the panel.